first one is just a short video, like 8 minutes, for different types of study skills or habits, or I forget exactly what they call them. So I would check it out if you want, if you're kind of looking for different ways to do things. And then the Math Center hours, I posted this schedule here, and I've highlighted the instructors that are able to do Calc 1, so you know what time to go. You'll see that not all times there's someone in the Math Center that can help with Calc 1, so hopefully you can utilize that to make a better decision as to when to go. Does anyone have any issues with my math lab? I hope that you're getting on that and trying to see if it's actually going to work for you, your personal computer or whatever you're using. Okay, so let me know if you have any issues with any of that. We did finish 2-1. I don't know if anyone started the homework, but are there any homework questions on 2-1? I'll try to remember to start each class with homework questions. So if you have questions on the homework, feel free to ask them at the beginning of class. If you don't want to ask, then email me beforehand and I'll just go over it in class. Cool? All right. We're in 2.2, and really the only thing we've done here in 2.2 is to talk about a preliminary definition of a limit, and then we looked at this graph here, figure 2.7, and we've computed 4 different things here. Okay, so the main idea was that, one, the limit doesn't care if the function's defined at a particular location. So for instance, I don't think we computed this, but like the x value of 3, our function f of x is not defined at 3, but we can define a limit as x approaches 3. Okay, so let's write that one out too on this figure. Let's see that. So we'll call this number 5. F evaluated at 3 does not exist. And 6, what would the limit as x approaches 3 on that function be?
4.
4? Do y'all agree with that? So remember, the limit is just asking, as x gets closer and closer to 3, what value on the function, what y value do we get closer and closer to? And so we're getting closer and closer to this y value of 4. So that's one of the biggest distinctions of when we compute a limit. I think we're used to, looking at a function and saying, hey, it's not defined here, so there's really nothing I can do at that location. But we can actually compute limits when the function doesn't exist or isn't defined somewhere. And in many cases, not in all cases, but in many. Okay. So does anyone have any questions over that? All right, then we'll move on to discuss one-sided limits. So the example we just did when we were asked to compute those limits were two-sided limits. We were just imagining traveling along the function from both sides. We can and do look at can define and do look at one-sided limits. So like, why would we look at, or why would we concern ourselves with one-sided limits as opposed to two-sided limits coming from both directions simultaneously versus a one-sided limit only coming from one direction?
Because sometimes it might not match up when you're coming from both sides. One side might be on a different scale or a different number than the other. Right.
Yeah. So like they might not match up in the sense that what kind of function have we seen before where the function isn't all connected? What do we call those?
Stepwise?
Piecewise, yeah. Piecewise functions. Do y'all remember those? So one of the reasons, so why even bother with these piecewise functions? And, you know, there's other types of functions, like if you think of the square root function, for instance, the square root function isn't defined for all real numbers, right? So, you know, various types of scenarios like that. And if you can remember, the square root function looks like this. So, domain 0 to infinity. It wouldn't make sense on a square root function, a logarithm, you know, those types of functions with restricted domains to look at a two-sided limit at 0, right?
Sure.
So if we're talking about a two-sided limit, we have to be able to approach it from both directions. And we see clearly on the function, there's only one way, one direction in which we can approach 0. So these one-sided limits are sort of natural in the sense of certain types of functions with restricted domains and goofy functions like piecewise. Okay. So if you'll notice, they've defined this in a similar sense of the preliminary definition of the limit. So I want to go back. I don't know if we sort of made this note here. This definition of the limit that we first started off with, this was a two-sided limit. Just so we're all clear, that's a two-sided limit. And if you'll notice, there's just a slight modification in the definition of a left limit and a right limit. So the right-sided limit is, as its name indicates, we're approaching some x value from the right and only the right side of that x value. So that's the right with x larger than a. So that's like this here. We have this value of a, and we're approaching a from the right or through larger values than what a is. Similar thing with the left limit here. The left-hand, left-side limit. You can't really see that, I don't think, but it does say on your notes x less than a. So we're approaching a from the left through values that are smaller than a. Okay. Is that clear enough? Anybody have any questions over the definition? Of course, we'll look at examples too, so. All right. Yeah, so let's just draw out a piecewise function here. So just whatever, we have these two pieces that aren't connected. We'll just say we have something like that. This is a x value of 3. And so at this point, it wouldn't make sense to say, what is the limit as x approaches 3 on this function? I mean, visually, we can see what's happening. Intuitively, what would you think about the limit as x approaches 3? Thinking in the sense of the one we just evaluated, we've evaluated a two-sided limit on figure 2.7. Maybe that can kind of incline you as to what would happen here. So remember, the sense of a limit is if x gets closer and closer to something, the question is, what is y getting closer and closer to, right? And we're going from both sides of that on that function, if you will. So clearly you can't approach, x can't approach 3 from both directions simultaneously, right? If you could imagine it doing that, what would the limit be? What would happen? Would the y values match?
No.
No, clearly not. The function isn't connected at the same y value. So this theorem here tells us what is the relationship between a one-sided limit and a two-sided limit. And what it says is, it's actually saying four different things, but it says that the function's defined at at all x values except possibly at a. And it says if the two-sided limit exists, and equal to some value, some y value L, if and only if, so that two-sided limit is equal to L if the limit from the left is equal to the limit from the right. IT's been notified about the crumminess of the projector, so hopefully they'll have that fixed before next class, but I don't know. We'll see. If and only if the two-sided limit exists, if and only if the one-sided limits are equal. And you always get multiple statements with an if and only if statement. I don't know how much time you've spent talking about the language when you read a theorem, but a lot of theorems just say, if this is true, then this happens, right? And so that's meant to be read that one way and only that one way. But when you have an if and only if statement, anytime you have an if and only if, it's meant to be read both ways. So not only can I read this, forward, if you will, and say if the two-sided limit is equal to L, then that means the one-sided limits are both equal to L. I can read that in reverse and say if I know the one-sided limits are equal to L, then I can imply that the two-sided limit has to be equal to L. And then you can flip that statement around and negate everything. So it's kind of just like an exercise in logic. Has anyone taken logic in like a philosophy class? Yeah. So I'll just write out basically the four things this one theorem is saying, because there's four ways to interpret it. Okay. So one, I'll just say here, theorem 2.1 states, one, if we'll start this way. If the two-sided limit is equal to L, then both one-sided limits are equal to L. So that's how the theorem sort of appears on the surface, right? But we can also go the other way and say if the one-sided limits are both equal to L, then the two-sided limit is equal to L. And then the other two we get is, if you could imagine taking those two statements, flipping the argument, and then negating them with non-equality, those are also true. So kind of the counter to that is if the one-sided limits not equal then the two-sided limit does not exist. And finally, if the two-sided limit does not exist, then, so if we know the two-sided limit doesn't exist, then we know that the one-sided limits are not equal to each other. So anytime you see like a theorem that's if and only if, it's a whole lot stronger of a statement than just saying if this, then this happens. And so all of those things are true based on that theorem. Does anyone have any questions on any of those pieces that we wrote down? Okay, so with that in mind then, let's go back up to this graph. What would the limit as x approaches 3 for this function be?
Undefined.
Undefined or does not exist, and why would it be?
Because both one-sided limits don't approach the same number or the same y value.
Okay, yeah, good.
Or you could say the two-sided limit it doesn't exist.
Yeah, it does not exist. So this thing will erase our question mark. And we'll say this thing does not exist. Why? For the very reason we just talked about here. In order for the two-sided limits to exist, the one-sided limits have to be the same. So we did this one here. Let's ask the question, what is the limit as x approaches 3? That totally changed. Let's try this again. As x approaches 3 from the right, what's the limit as x approaches 3 from the right? Oh, I guess I need some values. I was making this a lot more difficult.
It's a bar.
Let's say those are the y values. As x approaches 3 from the right? 5. Does everybody agree with that? We're approaching 3 from the right-hand side of 3. The y value is getting closer to 5. And the limit as x approaches 3 from the left? 4. Is 4. Does everybody agree with that? It's 4? So from the right. So we can see why the limit doesn't exist. Technically, the limit doesn't exist because 1 and 2 aren't equal to each other. Does that make sense? Anybody have any questions? So like what you'll see moving forward is most of the time when you're given a graph, not always, but most of the time, just looking at a graph, limits are pretty easy to calculate. So we want to move away from just graphing a function. Every time we have a limit on a particular function, it's super inefficient to graph that function. So we're going to ultimately move away from just looking at graphs to compute limits. And we'll see later on that even a table of values sometimes isn't accurate depending on the function. So what we're going to actually like work with eventually is like the algebraic or the analytic methods to compute limits for various types of functions. Because we don't want to graph, we don't want to just sit there and plug in values. Okay. All right, so does anyone have any questions on this before we move on? All right, this is getting a bit weird. I'm just trying to go down to the bottom. All the way. Okay. So just to point out, if we modified that piecewise graph just a little bit, and that other piece that we had up here was now here, going off in that direction. Would the limit as x approaches 3, the two-sided limit, would that exist? Yeah. So here the limit as x approaches 3 does exist, and it's equal to 4. Because as we approach from the left and the right, just like in that first example, we're honing in on the same y value from either direction. Okay. So like if you just looked at this like without the graph and we knew we were dealing with a piecewise function, and we said, hey, if I compute the limit as x approaches 3 from the right on some function, and I approach 3 from the left on some function, and that's also equal to 4, then just from these two pieces from the left and the right being the same, that tells us that those pieces that we initially maybe thought were individual or disconnected are actually connected. Okay. So figure 2.13, kind of a similar example here. First of all, what is this? Sorry, this is g of x. What is g evaluated at 2?
Does not exist.
All right, I heard 1, I heard does not exist. So the function at an x value of 2.
1.
So the function is defined here, isn't it? And that's a y value of 1. It's not defined on this piece, but remember these individual pieces make up the entire function. So just because one piece isn't defined at that x value doesn't mean the entire function is not defined there. So it actually is defined as 1. So part 2, what is the limit as x approaches 2 from the right? 1? What do y'all think? Is it 1? As we approach 2 from the right, we can only use this path, and that's a y value of 1. What about the limit as x approaches 2 from the left? Equals 4. Does everyone agree with that? So if we're approaching 2 from the left, we have to approach it in this direction. It's getting closer and closer to a y value of 4. Okay, so then what would we say? What would we say about the limit as x approaches 2 on this function? does not exist, right? And it doesn't exist because, right, does not exist since, we'll write it out mathematically, since the limit from the right does not equal the limit from the left. And so, you know, I would get accustomed to, you know, just reading this work, because eventually, like I said, we're gonna move away from the graph. I think it's important to be able to determine, okay, well, since 2 and 3, the one-sided limits aren't the same, that means this particular thing is not connected there. So we should be able to get to the point where we don't even know this information right here, but we can look at these two pieces and say, well, clearly they're not connected, because as I approach 2 from either direction, they're not matching up. So they have to be separate pieces. Okay. So any questions? All right. These, you know, I don't know, I think it seems like we have a pretty firm grasp on this. We can certainly come back to those if you think it's necessary. But in the next section, we're going to get certain techniques to compute limits. So moving away from like just looking at graphs. But the other thing we mentioned is, well, okay, if I give you a function and I say, what is the limit as x approaches 4? And maybe it's this weird looking function. Like maybe another intuitive thing you could do is say, all right, well, let me just get my calculator out and let me plug in values like 3.9, 3.99, 3.999, right? And just have your calculator get closer and closer to 4 and see what the y values output. Does that make sense? Like if you have a calculator and I ask you to compute the limit as x approaches 2 on, I don't know, the square root of x, then one thing we could do is just say, all right, well, here's an x value, here's the square root of x. Let me make x 1.9 and then 1.99 and so forth. And then so we would just calculate these values. What's the square root of 1.9? Anybody? .3784. What about 1.99? 1.999?
1.4139.
Okay, so then you could look at these values and say, well, at 1.9 it's sort of close to 2. I got a 1.37, 1.38 rather, 1.99, a little bit closer to 2, and it jumped to 1.41, a little bit closer to 2 again. It's still hovering around 1.41. So then we could make a guess and say, I would expect that the limit would actually approach, something that's approximately 1.41, right, based on what we've done. And so just take the square root of 2. 1.414. 1.414. Yeah. Let's just say approximately here. But in a lot of senses, you can get an idea, a clear picture rather, of what that limit is just by plugging in numbers either to the left or to the right or both. So oftentimes numerical analysis does work for computing limits, but again, it's really inefficient because how close can we get to 2? As close as we like, right? I can just keep adding 0.9, 0.9, right? And that's successively closer and closer to 2. So 1, we don't have a full picture. And you know, if we had 10 values, we'd have a fuller picture, but that's just time consuming to look at those, right? And the other thing is it doesn't always work. Like looking at a numerical analysis of limits doesn't always work. And we'll look at a function here that'll show that it doesn't always work. So I guess this function that we're going to look at will sort of answer the question, why. Can we not just graph or look at a table of values? A limit. And you know, again, we've seen instances where it works, but there are instances where it doesn't work or where these methods fail. So what we want is a legitimate way to answer questions about limits that's applicable to any limit, right? We don't want to just say, okay, hey, for these, graph it and then see what the limit is. For the functions like this, just look at a table of values. We want a comprehensive way to tackle limits. And we're going to consider the function f of x equal to cosine of 1 over x. And so, like, if many of you coming from pre-calc, for calculus and onward, your calculator should be in the radian mode. So make sure you're in radians from now on. So we're going to look at the function cosine of 1 over x. And ask, so the question is, what is the limit as x approaches 0 on this function? So I don't know about you, but I don't think that's, you know, something that is just in our minds on how to graph. If it were cosine of x, it would be pretty straightforward. So let's just go ahead and look at the graph in an easier way. Oops. And so we see it's not much better, right? We're trying to figure out what is this limit here at 1, but at 0 rather. But as we get closer and closer to 0, things don't improve. Right? So the graph is useless. It does look like it's completely solid, but you know, as we get closer and closer, see if we can, oops. As we get closer and closer, you can see that there is spacing between these things. The thing is it's just the oscillations are getting much more rapid. So eventually it just looks like a solid fill. So, you know, outside of 0 might be, the graph could be somewhat useful, I think. But at 0, what we're trying to figure out, it's totally useless. Okay, so graph, no good.
Is there a way to figure out the limit of that?
Yeah.
You can't really interpret from the right or left side either.
Yeah. So the thing with the limit, right? We can see the function 1 over cosine, or cosine of 1 over x rather, as a function just by itself, cosine of 1 over x isn't defined where?
0.
At 0. But can we compute the limit as x approaches 0 on a function that's not defined at 0? So could we had this function here that wasn't defined at x equal 3, but could we compute that limit as x approaches 3 from the left? Right. So even though the function is not defined at 0, we can still say as we get closer and closer to 0, the y values get closer and closer to what, if anything, right? So again, that's just a big difference between a function value versus a limit. So let's try then a table of values. So we'll calculate a few values to the right of 0, just to see if we can get an idea. So we'll have x, and then we'll compute cosine of 1 over x. And let's say x is 0.001. And we'll also compute 0.0001 and 0.00001. So again, calculator in radians, let's take a second or two to compute those. Oh, by the way, did anyone not get a handout from the first day?
I'll need one.
This is the first and last page of the syllabus. Contact information. To class. And I don't have to. However, 2.4, maybe during break if you want. 2.3.
These are
All right, cosine of 1 over 0.001 is what? 0.56237. Yeah? Look all right? Okay, 0.0001.
Negative 0.952155.
Negative 0.95.
215.
Do y'all agree? Is that what y'all are getting? Okay, and 0.00001. Negative 0.9. 936. Okay, so, you know, I mean, somewhat close to 0.
119.
Yeah.
Okay, 99936. That. So we're pretty close to 0. You can get closer, of course. But let's just stop here and see. If we did stop here, what might we think the limit is? Negative 0.999999999, which is negative 1. Right. So okay, let's just pretend that we stopped there, and we said, it seems like these values are approaching negative 1. So I'm just going to take a couple more values from the textbook, just so we can see what's happening here. So if we went a few more, then we would see the 1, 2, 3, 4, 5, with 5 leading zeros. It's really 6, but then we're back up to a positive 0.9. Then we're down negative 0.907. Even closer to 0 from the right, we're at negative 0.3. So we just see those values are just oscillating between positive and negative. They're not honing in on one particular value, right? So this isn't actually the limit. Yeah.
Could you use the unit circle? Or does that not work on this one?
Yeah, so that would be, well, like, how would you think about it?
Well, I know something divided by 0 is undefined, but I guess you could say cosine of 0 is equal to 2 pi, or pi, if you just plugged in, if you know that cosine of 0 is equal to that by looking at the unit circle.
Yeah.
Even, it may be undefined, but
So we could say that the cosine of 0, well, what did you say? Sorry, 2 pi?
yeah, I think it's 2 pi or 2 pi.
Well, cosine is 0 at, where? Where? Yeah, which is, well, cosine is, at 90 is pi over 2, so cosine is negative 1. Pi over 2, 90, yeah. So it's 0 and at 0 at 90 and
270.
yeah, 3 pi over 2. But that's cosine of that value, right? It's not cosine of 1 over 3 pi over 2 or pi over 2 or whatever we're plugging in. So yeah, table of values, useless, graph, useless. Granted, we don't look at a whole lot of functions like that, but it's just, this is just a really good example to illustrate that both routes fail miserably, and that we do need other methods to compute limits. That's kind of the whole point. That's the whole point of that example. So that's kind of what we see from 2.3, 2.4, 2.5. 2.4 and 2.5 are really dealing with more specific types of limits. 2.3 is where we get tools to evaluate limits. So that'll be a segue into section 2.3. Do y'all have any questions on any of that? All right. Well then, say that here. Do you'll need some more time to copy anything down, or are we good? So in 2.3, we're going to look at techniques for computing limits, and we're going to cover like the basic functions, linear functions, polynomials, rational functions, and we'll look at some other, I guess, maybe we can call them algebraic and non-algebraic. I don't know. So everyone remembers hopefully linear functions, polynomials. What's type or example of a polynomial function? I'll give you a hint. Any linear function is a polynomial, but what else is a polynomial?
Like x squared, x cubed.
X squared, x cubed, any combination thereof. 5x to the 5th plus 12x to the 4th. Rational functions are what?
Straight facts.
They're-
Division, 1 over x.
Like 1 over x, yeah. Rational functions are when we take polynomials and divide them. So like 1 over x, x squared plus 2x over x cubed minus 1, those are rational functions. So hopefully you remember those, because a lot of the stuff that we're going to do with limits, like on rational functions in particular, and sort of justify, like why we have a vertical asymptote there. Where is the horizontal asymptote? Well, where is the horizontal asymptote located? And we'll get into that later in this chapter, but the first thing we actually address is just from a theorem, and it says that if we compute the limit on any linear function, hopefully that came out a little bit clearer, but it says the limit as x approaches a on f of x, where f of x is a linear function, is just equal to f of a. So in other words, for linear functions, to evaluate this limit, all we have to do is plug in a. Into the function. And we call that direct substitution. We're directly able to plug that x value that we're approaching into the function. It doesn't, we don't have any restrictions, so I mean, hopefully that's pretty straightforward. If, I have some linear function, wherever it is, and no matter what value I'm approaching, it's all connected, so I can approach that value from the left and the right. I guess we'll just call that L. So no matter where you're at on that line, you can approach any x value from either direction, which is just, in this case, if I ask you what f of a is, you would just say, well, f evaluated at a is just L, right? But we've already seen that the function value and the limits aren't always the same. But what we're saying is, on a linear function, the limit and the function values are the same. So any linear function, for example, what's the limit as x approaches 2 on 4x minus 2? 6. Do you all agree? Again, we're recognizing this function. A lot of this limit stuff is like recognizing the function. We could sort of work our way around having to remember a whole lot of theorems and properties. If we can just remember, oh, hey, this is a certain type of function, and I just know from prior knowledge that this function, like for instance, has a vertical asymptote somewhere or whatever. So we're just going to plug 2. It's a linear function. We just plug 2 directly in for x. We'll just put this 2 in red here. Also, constants are linear functions. So like the limit as x approaches 3 on the horizontal line at y equals to 5, what would that be? 5? What do y'all think? So it could be helpful just to think about the graph. Here's a y value of 5. Here's our line. There's x equal to 3. The y value is always 5. So even though there's nothing to plug in here, anytime you compute a limit on a constant, it's always just that constant. we'll just say the limit as x approaches a on c is equal to c, where c is a real number. So as we'll see, there's some functions we can just plug directly into to evaluate the limit. Oftentimes we can't do that because the function's not defined at that particular location. The functions we can, like linear functions where we just directly plug into, we'll sort of talk about the concept or the notion of why we can do that in 2.6. All right, any questions on this stuff? So the limit laws, does everyone have that in their 2.3 that they printed out? If you did print 2.3 out, are those there? Okay. For whatever reason, they didn't show up in mine. I just need to make these a little bit bigger. So these are, it says limit laws, so I guess you can say laws or limit properties, like how do limits behave when they're interacting with certain types of operations? And then that's spelled out here in 1 through 7. So, you know, these combinations of operations, we've got adding and subtracting, we've got multiplication, division, and we've got, you know, powers and roots. So it really takes care of the basic algebraic operations as far as how limits interact with those operations. So the sum is just saying that if you're taking the limit of a sum, that it's the sum of the limits. If you want to think about that limit operation distributing across the sum or distributing across the difference, then you can think of it that way, because that's essentially what's happening. Does anyone need this? So you don't have to write it down. I did make copies of that particular thing. It's just a lot to write down. Maybe extra left. Just pass it down if you want. Okay. Again, like you know, I would, if you didn't have this printed out, I wouldn't necessarily worry about writing that down because these notes will be posted after class. I'll just go directly into kind of just, I guess, illustrating these with a specific example. So like the limit as x approach 2 on, let's just do x squared plus x. What we could say is that that's the same thing as computing the limit as x approaches 2 on x squared plus the limit as x approaches 2 on x. So in practice, after you've maybe seen a few of these or done a few of these yourself, you don't necessarily need to write this step out here, because more than likely what you're going to do is kind of, for these ones that are more straightforward anyways, you're probably just going to do this in your head and say, all right, well, if x is 2, then it's 2 squared plus 2, right? But we're just going to illustrate how the laws work and maybe look at one example of like breaking it down. But in practice, you don't usually break them down this way. It's helpful sometimes to break them down this way to maybe look at it in a more conducive way. But in practice, you generally don't write all of this out. Okay. 3 is the constant multiple. So it just says if you have a constant multiple times a function of x, like the limit as x approaches -1 function 3x. Again, we can look at that in a couple of ways. One, we know 3x is a linear function, so I can just plug the -1 directly in for x. But the law just says that that constant multiple of 3 can come out and multiply this here. Okay. So, the limit as x approaches something, you gotta think about that limit as an operator, and it's operating on things that involve x. It doesn't operate on the 3 multiplying the x, right? It's just operating on the x. Product rule says that the limit of a product is the product of the limits. So like the limit as x approaches 4, 3x times the square root of x is the same thing. We can compute it as the product of the limits. Again, in practice, what you would do is probably just try to plug x at 4 and just multiply the result. But does anyone have any questions on this? Hopefully it's pretty straightforward. Yeah.
The power one doesn't really seem like it does anything.
Yeah.
That is normal?
Yeah, and it's kind of similar to the constant multiple, right? The limit's operating on x, so like we can compute the limit first and then raise it to that power. Is basically what it's saying. So the quotient, just keep in mind there's a restriction with the quotient, and it's just the same restriction you've always had when you take the quotient of two functions. You can't divide by 0. Okay, so like the limit as x approaches 1 on x squared plus 2 over x plus 1. We could write that as the limit of the numerator divided by the limit of the denominator. So that's plus 2 on top. And then compute those separately, and then take the quotient. Again, we can do this provided that this limit on the bottom isn't 0. We alluded to that last class, I think, sort of maybe indirectly, but just think about if your numerator was 5, let's say, and the denominator is approaching 0, what would happen to your quotient? What's 5 over a number that's getting smaller and smaller and smaller? So like a number that's getting smaller and smaller, we could start out with 1/10, and then 1/100th, and then 1,000th, and so forth. But what would happen to the overall quotient? It would get bigger, right? So when the denominator of these quotients approaches 0, we'll address that in mainly in the next section, but there's some other kind of caveats there. Okay, the power rule, I think, is next. Yeah, the power rule just says you can pass the limit through a power of x. So like if it's the limit as x approaches -2 on x to the 4th, I can compute the limit as x approaches -2 on just the function x, and then raise all of that stuff to the 4th power. So yeah, I mean, there's nothing mystical happening here, because if I plug in -2 for x, I have to raise it to the 4th power, versus the one we wrote on the right, well, x is -2, and then I raise it to the 4th power. Kind of the same thing. And again, we see why that works more so in 2.6. So a little bit more justification in 2.6, but that's that. And then the root, notice the property for the root, it says that the limit is, like the power here, the limit is able to pass inside the root, provided that the function is greater than 0. Because that, the 1 over n, it says if n is even, right? So this specifically is talking about even roots. And we know that the argument, or what we're taking the even root of, has to be positive or 0. Otherwise, you get an imaginary number. So nothing, you know, the algebraic laws of what we know, dividing through by 0 and even roots of negative numbers are still holding here with these laws. So like x to the 1/4, the limit as x approaches 4, it's exactly like the power rule. Or if you want to look at it this way, same thing. So, you know, technically roots are powers, we just have to be considerate when we're looking at an even root. And that's why number 7 comes in. It's specifically addressing even roots. You know, another thing to mention is that if it kind of like escaped your mind, I think like as you're doing it, it would be totally obvious. Like, oh hey, wait a minute, something's goofy here. Like if you were computing this limit, you would say, well, can I do this? And then pass that through the 1/2 power. So at some point, just from an algebraic standpoint, you should recognize, hey, there's something funky happening here. Does anyone have any questions? So with these limit laws, we're gonna like build our functions. So we've got a linear function. We're gonna use these limit laws to look at one polynomial function and then make a general statement about that. And then look at rational functions because that's in line with property number 5, like when we start dividing polynomials. And then we'll look at, you know, more, I guess, weird functions or exotic functions and compute limits for those. Questions before we go on break? All right, let's take 10 minutes. Okay, so we'll go on through 2.3 here. And like I said, we're going to use those limit laws to look at an example of a polynomial function, taking a limit. But again, like you don't have to write all of these steps out when you're evaluating a limit.
Question.
Just so we can kind of piece all of them together, because they all work in conjunction with one another, not just individually. So the way we can break this down is, first of all, the outlining structure of this function is it consists of a bunch of functions of x added and subtracted from one another. So we'll just separate the addition and subtraction first, and distributing the limit to each term, if you will. And the last two terms, or the last two limits rather, are boiled down basically as far as we can. The 2x squared, we've got a constant times a function of x, and we've got a power on x. So we can pull that constant out front, compute the limit as x approaches 1 on just x, and then square that. Make sure you're just squaring the limit on x, because x was squared, 2 wasn't squared, plus the other two limits. So, you know, in a sense, with those limit laws, what we've done is we've taken a polynomial function and boiled it down to now just isolating the limits or just looking at the limit pieces. They're all limits on linear functions. And then from that other theorem, we know like to evaluate a limit on a linear function, all we have to do is plug the thing we're approaching in for x. So what we have here is we have 2x approaching 1. We're going to plug that in for x. So it's 2 times 1 squared. Plugging the 1 in again for this x. And the limit as x approaches 1 on the function 2 is what? Is 2. So we have 2 plus 1 minus 2, which is 1. Let me write it down. Okay, so the polynomials functions can be broke down by the limit laws to just limits of linear functions. And again, linear functions can be evaluated by direct substitution. But what we're seeing here is that this is the same as just plugging in x for the original function without sort of breaking it down piece by piece. Same thing as just plugging 1 directly into that. So then, you know, we could do that with other polynomials, but I think the point is illustrated. Stated in this theorem, part A, it says if p of x is a polynomial, then the limit as x approaches a on any polynomial function is evaluated, again, by direct substitution. So that's our little note here. We compute a limit on a polynomial using direct substitution. Just plug that in. Is that all clear? Does anyone have any questions about that? And you know, it may seem like we're taking really small steps here, but it's sort of congruent with if we were the ones that came up with all of this stuff. Like we would have to piece it together this way. So that's kind of why we're working through it that way. It's like, all right, well, we've solidified linear functions and their limits. We've solidified these laws. We would have to prove all of those laws and give it to other people and say, hey, is this right? And they're like, yeah, it looks good. And then we publish it, and then everybody accepts these laws as truth. And then from those laws, we start with polynomials and say, hey, it's just direct substitution again. We're going to make a statement about polynomial functions, and then we're going to prove that. And then that's universally accepted. And we say, now we have polynomials, let's move on to rational functions because we've got a limit law that tells us how to deal with division. And we have polynomials. So what happens when we divide two polynomials? So it's like this sort of natural progression on how things would have actually unfolded if we were the ones that discovered this. I know it's probably not all that exciting, but we are bypassing a whole ton of work by just saying, hey, this is true. If anybody ever goes on in math, does anyone plan to major in math at all? Yeah. So you'll end up taking a class that they call analysis, where you start with a general statement like this, and you have to prove it, and it's no fun. So then we've got polynomials now. With this theorem too, it says, and notice that it's kind of similar to what we said for the quotient rule or the limit law with quotients rather. But the difference here with this rational function statement, theorem 2.4 part B, and what we had in our limit laws, does anybody see a difference between those two? Quotient number 5 and limit law, or theorem part B, 2.4 part B? Subtle. Yeah, visually, yeah, for sure.
Can't divide by 0.
Yeah, it's still provided that the limit on the bottom's not 0, right? So the difference is that this quotient property or law, notice that they just say f and g of x, and they don't specify what those functions are. So this is more broad. It applies to any quotient. But when we go down to this theorem and it says part B, rational functions, what are p of x and q of x?
Not 0.
Polynomials. So this one's specifically dealing with polynomials, not two generic functions divided by each other. Okay. Still the same thing is present though. The bottom limit, the function on the bottom, can approach 0. We'll see that it actually can, but it's a little bit different of an analysis that we have to do. All right, so then we'll move on to rational functions. And again, I think having prior knowledge of rational functions, prior working knowledge, most of you have seen rational functions, but many of you probably forgotten how you reasoned through those to generate a graph and stuff like that. But that's definitely worthwhile to review. So we're going to just look at a couple. Here we're going to evaluate the limit as x approaches 1 on 2x squared plus x minus 2 all over 4. So just like ignoring the limit as x approaches 1, if that were a function by itself, whenever you're dealing with those functions, as far as x is concerned, what do we have to worry about? What can we not do? Have 0 in the denominator, right? So if just think about it this way, I'm asked to compute this limit as x approaches 1. If I plug in 1 into the denominator, is that going to cause any issues? No. For the second example, if I plug 2 into the denominator, is that going to cause issues? Yeah. So in example 2, we have to sort of reconsider how we're approaching that problem. But in example 1, we don't have division by 0, or we don't have the bottom function rather approaching 0. So there is no issue here with just directly evaluating this. So again, to see that, let's write it out as the limit as x approaches 1 on the numerator divided by the limit as x approaches 1 for the denominator. And remember, the theorem says that we can do this provided what? Right, the denominator, the thing on the bottom doesn't approach 0. And that's not the case here. So if we just look at now the numerator and the denominator, we're just computing the limit on a polynomial divided by another limit on a polynomial, and we know how to handle those. We just plug 1 directly in for x on the top and 1 in for x on the bottom. And then we evaluate that. So we have 1 over 5. So remember, what that's showing us is that if we looked at that function, and we approach, as x approaches 1, we're just saying that the y values are approaching 1/5. So if we can get there, we can see that it's 1/5, and this is our function. So even a function like that, if you can remember all the steps involved in graphing it, right? You have to find the intercepts, the asymptotes, both vertical and horizontal. Are there any holes in the function? Right? There were several components to graph that, but so much more efficient to be able to do this as opposed to graphing it. So then, in example 2, we've got this issue of the limit in the denominator is approaching 0. So if we write it out like we did this last one, oops. And we compute this limit, we're going to get 0 on top, 0 on bottom, and even if we tried that property and forgot the restrictions, well, now we're in a place where we clearly see that there's an issue, there's a problem, right? So that's evaluating it this way isn't going to work out for us. By the way, 0 divided by 0 is not 0. Remember, in the sense of a limit, what that means is the top, the numerator, is getting smaller and smaller, and the denominator is getting smaller and smaller. Like if the top is, the numerator rather, is getting smaller at a faster rate than the denominator is getting smaller, it's not going to be 1. If they're both approaching 0 at the same rate at all points in time, basically, then it would be 1. Like a really small number divided by a really small number isn't 1. So what are the other tools that we have to deal with something like that?
Well, you can multiply by the conjugate of the denominator to cancel out like your, you know what I'm saying?
The
Like you can square your denominator.
So what would you multiply by?
X plus 2.
On the top and the bottom?
Yes.
So does everyone remember this term, the conjugate? The conjugate of A plus B is A minus B. So is that going to help us here? So we have some polynomial up top. So basically think about it this way. Initially I can't evaluate this limit. Why? Because this thing in the bottom is approaching 0, right? That entire thing, the x minus 2, is giving me problems. So yeah, the function isn't, this function is not defined at 2, right? Because I can't plug 2 directly into this function. So multiplying this is totally valid algebraically. The question is does it help us? And the answer is no, it doesn't, because I still have that issue of the x minus 2 hanging out in the bottom. This algebraic process did not get rid of x minus 2.
You can tell, or I guess x squared minus 4 is really x plus 2 times x minus 2. Then you can cancel out the x minus 2's.
Yeah,
Denominator. And numerator.
exactly. These types of instances where initially it appears we're dividing through by 0, a lot of times we just need to try to simplify the function to see if that problem goes away. So we're going to factor the numerator. It's a difference of squares. So we're going to do this. And then hopefully now we see exactly what happens. The factor x plus 2, more importantly, the issue in the bottom, sorry, x minus 2. I wrote that wrong. The x minus 2, rather, that issue has been removed. And so that's just algebraically equivalent to computing the limit as x approaches 2 on the function x plus 2, which is what? Right, it's now a linear function. So hopefully, if not, you can look over rational functions, but you remember, in the sense of a rational function, forget that we're computing a limit. When we factor stuff on a rational function and factors in the numerator and denominator cancel, what does that give us on the graph? A hole, right? It's a whole because the function x squared minus 4 over x minus 2, that function is not defined at an x value of 2. But we see that that function, x squared minus 4 over x minus 2, is identical, in a sense, to the linear function x plus 2. Okay? So let's, just to see that, let's graph x squared minus 4 over x minus 2. So doesn't that look like the line x plus 2? Same line. Well, let me put that back. What is the difference? What's the difference between the function, the rational function, and our linear function? How do they differ? The whole, right? The rational function has a hole on it. So when we graph this rational function, yeah, we're graphing the line, but that line has a hole on it. That's the only difference. So if we turn this off and we go towards, well, we get closer here. We're approaching 2. If we approach an x value of 2, notice this is 0 or 2 undefined, rather. So that's the function that we're actually computing the limit on. We're not seeing that hole. We do see that through the work. We don't see it on the graph itself. But if we graph the linear function x plus 2, we know perfectly well that it's defined at x equals to 2. So what I have here is just kind of a general statement. It doesn't necessarily have to be a rational function, but if the function that's sitting out in front of the limit is undefined at the value a, which x is approaching, if that function is undefined there, but you are getting a finite limit, then that always means you've got a hole there. That's the only other option. If your function's undefined somewhere, but we do have a limit, it has to be a hole, right? There can't be any other thing going on. So I just wrote that out generically. If the function's undefined at x equals to a, where a is a finite number, then the limit, if we compute the limit on that function and it's equal to n, then that original function has a hole at the location a comma n. So this function that we've just computed this limit on, this function, based on just this single line of work, has a hole at x value of 2 because x is approaching 2, y is approaching 4. And maybe that's not simpler in an algebraic sense, because in an algebraic sense they said, hey, if you've got a factor that cancels, then you've got a hole there. But you didn't have a hole at negative 2, right? You had a hole at the corresponding 0, x equals to 2. And then you had to plug that 2 back into the reduced function to get the y coordinate of the hole. So we're kind of doing all of that at once. And the reason we're able to explain it that way in algebra is exactly based off the idea of a limit. It's all based on a limit, why there's a hole there, and where that hole is located. I don't know if you remember did they ever refer to a hole as a removable discontinuity? Do y'all remember that? So you can see why that's the case, because the place where the function's not continuous, we have to pick up our pen to graph that function. The place where that function isn't continuous got removed. And we ended up with this simpler function that still represented this function with a hole in it. And so the idea is, well, how can we cancel this? You know, how can we cancel x minus 2 over x minus 2? Is x minus 2 over x minus 2 always equal to 1? Does x minus 2 over x minus 2 always equal 1? No. When does that not equal 1?
2. It's 2.
When x is 2, right? Because when x is 2, what do we get? When x is 2, you have 0 over 0, and 0 over 0 is 1. right? Remember, we just talked about that. The top's getting smaller and the bottom's getting smaller. Doesn't mean they're getting smaller at the same rate. Yeah.
I don't know, we haven't started yet, but I was wondering if we're gonna do Le Hôpitals or...
Yeah.
Okay.
Yeah, that's at the end of chapter 4. Yep. That's super powerful tool, I guess. So yeah, the idea is, since now with this rather, the idea is, well, we're just computing the limit as x approaches 2. The limit as x approaches 2 doesn't care about what's happening at x equal to 2. So the fact of the matter is, since we're tacking this limit on, x minus 2 over x minus 2 is always 1, isn't it? Because x never really gets to 2. We said that this thing that we've canceled out is always 1, except when x is identical to 2, but that sort of belies the very definition of what it means to take a limit. We get closer and closer to 2. X is never actually equal to 2. So then this factor that we've canceled out is always 1. If we didn't have the limit there, so like that's really the issue they never address in algebra. If we didn't have that limit there, and somebody said simplify that, and you said it's equal to 1, but it's not a true statement. It's not always equal to 1. The only time this is equal to 1 is in the sense of a limit. If you're getting closer and closer to this, of course, if you're getting closer and closer to 1,000 or 100, it's totally a trivial thing, because 100 minus 2 over 100 minus 2 is still 1, right? But it's really this limit that is dictating how this kind of unfolds. Does anyone have any questions? Sorry, that was kind of long-winded, but whenever possible, if I can tie it to something that you've already learned, I'll try to do that. Okay, so the function's undefined as x approaches a finite number, but you still get a limit in return that will always give you a hole at a comma whatever your limit is. Okay, a couple of other strategies. So the conjugate was mentioned, and the conjugate is an important simplification tool when you're dealing with radicals. So the importance of a conjugate, I'll end up erasing this, but you can write it out if you want. When we say a plus b times a minus b, these are conjugates of each other. And the reason this is more advantageous when we have radicals or roots, specifically square roots, I guess, here in this example, but when we have roots is because we know that this ends up giving us a difference of squares. And so if we have these radical things in here, like x minus 1, or square root of x minus 1, times the square root of x plus 1, well, we know this thing's going to get squared, and this thing's going to get squared, right? So we're eliminating the radicals when we utilize the conjugate sort of in this form. So I guess I'll leave that here, but we'll see this. This is pretty much our work here for this part. You can FOIL this out if you want, but it's the first thing squared minus the second thing squared. Okay, so the issue with the limit again is that the bottom or the denominator is approaching 0. And unlike that last example, at least maybe on the surface, we can't factor this, right? So it's like, okay, well, factoring's not going to work. What else can I do? I can try to get rid of the radicals by involving the conjugate, and that's exactly what we're going to do. So 100% of the time, you have functions that, no, I don't want to say that. The vast majority of times you have functions that involve radicals like this, you're going to use the conjugate to simplify that. So that's what, we'll leave this piece here because that is our conjugate. So how is that helpful? Well, again, the issue on this, computing this limit comes from the what do we call it, factor, I guess, on the denominator. If I can remove or get rid of that factor of x minus 1 on the bottom, which means I need a factor of x minus 1 on the top, then I can compute that limit, just like that last problem. Okay, so then we're going to say that the limit as x approaches 1 on this function, sorry, x minus 1, and we're going to multiply by 1 in the form of the square root of x plus 1 over the square root of x plus 1. So again, the conjugate gets rid of radicals. The problem, x minus 1 in the bottom, doesn't involve a radical. We also need an x minus 1 up top. So, you know, this is really the only option at this point that we have, is to try to get rid of the radical so we have an x minus 1 on top. All right, so the top we've already multiplied out. It's the first thing squared minus the second thing squared. We're in a different color. Over. Now here's the thing, the issue, the factor of x minus 1, we want to eliminate that. So you definitely don't want to multiply this out on the bottom. You would just want to leave it factored. The thing that's causing you problems, typically causing you to divide by 0, you want to leave that out. You don't want to take the thing that's causing you to divide by 0 and multiply it in through a bunch of stuff, because then you lose that information. Okay. So we're just going to leave this factor of x minus 1 times the square root of x plus 1 on the bottom as it is. All right, and that way we can clearly see what cancels and what's left over. If we were to multiply the x minus 1 through the square root of x plus 1, then you've got 4 different terms, and it's super unclear as to where that x minus 1 actually is. So the issue in the denominator we're always going to leave alone. And then we can see now, like that last example, that factor cancels out. So then we're just computing the limit as x approaches 1 on 1 over this thing, square root of x plus 1. So then as x approaches 1, are there any issues? No, we got rid of the issue. So we're just going to plug 1 directly in for x. To get 1/2. So was the original function defined at x, the value we're approaching? The original function. Is it defined at x equal 1? No, right? Because x equals 1 causes us to divide by 0. The original function is not defined at the value we're approaching, but we do get an actual limit. What does that mean about this function? It has a hole where?
1, x equals 1.
Comma.
1/2.
1/2, right. I guess I should be a little bit more specific here. Has a hole at 1/1/2. Just like with the rational functions, the issue, that place where we're dividing through by 0 got divided out. It got removed you have a hole there. So square root of x minus 1. That was it, right? Yeah, so that was it. So there's that function, we're approaching 1. So notice this thing says, if I can get it there, this thing says 0 undefined, so that's not helpful. What is this y value that we're at right now? 1/2. Does anyone have any questions on that? So when you see radicals and limits that aren't working out, then typically you're going to default to using the conjugate to simplify that algebraically. This second method that we're going to mention, it doesn't always work, but when it does, it's probably a little more efficient. The factoring in a sense comes from like looking at our work with the conjugate here, kind of in reverse. So if we know that this thing times this thing is x minus 1, then we know x minus 1 can also factor as the square root of x minus 1 times the square root of x plus 1. In other words, we're looking at the factor on the bottom as a difference of squares. And typically those linear factors like x minus 1, x plus 5, we don't, or x minus 5 rather, we wouldn't consider those differences of squares because x is kind of in its lowest form. But algebraically, we could certainly write x minus 1 is the square root of x minus 1 times the square root of x plus 1. Right? Does everybody agree with that? Just multiply that out, you can totally verify that it's true. So that's all I'm going to do. I'm going to just rewrite the limit with the denominator factored as such. And we see once we do that, we're exactly where we ended up with as the limit as x approaches 1 over square root of x plus 1, which was what we just computed. So there's our hole at 1/2. Again, that method doesn't always work. Does anyone have any questions? Okay, so just real quick, something like this, if you can kind of get the pattern of when you can factor versus when you can't, can be a little bit more efficient. Otherwise, you would see, hey, x is approaching 9, causes me to approach 9 in the denominator. I've got an issue there, there's a square root involved, I should use the conjugate. But otherwise, we would say x minus 9 is a difference of squares as the square root of x minus 3 times the square root of x plus 3. So just, similar to that last example, the x minus 3's, or sorry, root x minus 3 cancels out. We just have this. just to really quickly give you another example of where that factoring would work. That's part of the function, I just ended up graphing it, but with this. As x approaches 9, the original function is not defined, but we do approach a finite number, so there's our whole, it was 1/6 here. So just, if general things work for you, if you have, maybe we could write something even more general than that, but this is kind of the form we're dealing with, x minus a number squared. We can factor that as the square root of x minus a times the square root of x plus a. Or even x minus a, we could factor that as a difference in squares, square root of x minus the square root of a times the square root of x minus or plus the square root of a. So some people like these general statements, other people don't. I know for myself, the longest time when I saw stuff like that, I'm like, what does that mean? Give me something specific. But if that works for you, then there it is. All right. Okay, so the next example will illustrate where factoring doesn't work. So the limit as h approaches 0, we've got the square root of, I guess we could try to factor it, but 196 plus h minus 14 all over h. So here, clearly the denominator h is approaching 0. That's a problem. We need to try to simplify this. There's a radical involved, so we should default to the conjugate. Remember, the conjugate is specifically here with radicals. It's the radical portions of those functions, so we can get rid of the radical itself. So the conjugate here that we're going to multiply top and bottom by would be what?
Square root of 196 plus h plus 14.
Right, good.
Times that.
Yep. So the conjugate, remember, just anything that I separated with a plus or minus are conjugates of each other. So we've got to view this term right here as a minus 14 is our b. So this is, to simplify this, we're just going to multiply by root 196 plus h plus 14 over the same thing. All right, just like those other examples we looked at, the h is the issue in the bottom, so we don't want to multiply the h through. If we did, then you would just have to factor it right back out. So at the denominator, we're trying to cancel that h on the bottom. We're going to leave alone. We're going to multiply out the numerator. And what do we get when we multiply the numerator out?
196 plus h minus 196.
Right. So the first times the first, the square roots undo each other. So it's just 196 plus h. The cross terms, I don't know if you use FOIL, the O and the I are same but opposite in sign, so they're 0. And then the last times the last. So we have minus 14 squared. So minus 14 squared is 196. So lo and behold, we just end up with an h up top, which will cancel the h on the bottom. just combine like terms in the numerator, left with h. That h cancels. And we have now an equivalent algebraic function, or function algebraically, that doesn't have any issues as h approaches 0. Now, some people like to look for patterns and say, like if it starts out like this, then it's going to end up like that. I think there's nothing wrong with looking for patterns. It's kind of a shortcut. I would focus more, if you can recognize it, then that's fine, but I would focus more on the process. The process is always more important. And on an exam, I might ask why or how do you know that. So we've clearly shown why or how here. What is this limit now?
What's the answer?
Yeah, what's the answer? 1 over 28, yeah, because we can evaluate this now, right? We're going to say that when h approaches 0, let me just plug that in for the h. So I'll do this. The h approaches 0. We can now evaluate this directly. So we're going to plug in h as 0. That's what h is approaching. We get 1 over the square root of 196, which is 14, plus 14. That gives us 1 over 28. Does anyone have any questions? So what's true about the function that we started off with?
As a whole.
As a whole, where?
0, 28.
Right, good. Original function wasn't defined at 0, but the limit as we approach 0 ended up as a finite number. So this function as a whole at 0, 1 over 28. Okay, example 4 is another situation you've encountered in algebra. So the way we're going to simplify these types of functions is an algebraic method. And like I said, most of what you see in calculus is it's like 20% of calculus is, hey, this is what, I don't know, this is what a derivative is, and here are the derivative rules. And then computing a derivative and simplifying and solving, that's like all algebra. So a bulk of this class is algebra, probably more so than it is calculus. It seems weird, but. So when we have these complex fractions, how do we simplify those? I mean, I guess there's a couple of ways. One is definitely more efficient than others. But any suggestions on this right here? The bottom is approaching 0, so we've got to try to get rid of this factor of h in the bottom if we have any hopes to compute that limit. Okay, so one thing we can definitely do is try to add what's on the numerator, right? But you would still have a fraction within a fraction. So we're gonna, this time instead of computing the limit like we did in a single line, we're just gonna take this expression with that function and simplify it first and then compute the limit. Okay, so we're gonna take this and simplify to see if we can get rid of this factor here, this h in the bottom. So we can add the things up top. but we would still have, we would still have something of the form, something divided by something all over h, right? And then when we have a fraction divided by a single thing, that h is really going in the denominator here. So that's like, we can turn this into, something over h times something, if we added those together. Yeah? The easier way is to do what? Did anybody come up with something? So if we set this equal to 0, we're asking ourselves, what values of h cause this whole thing to be 0? It's true that h is getting closer and closer to 0, but that doesn't mean we care about where the entire function is going to be 0, right? Kind of a different thing. So the trick here is the lowest common denominator. It's what you have to find when you add these things anyways. So since you have to find the lowest common denominator, if we're going to subtract these things, we might as well use the lowest common denominator to clear the fraction for us, instead of adding it first and then trying to get rid of the fraction. So the lowest common denominator here is 9 plus h times 9. And if you're, I know sometimes it's tedious to find the lowest common denominator. So what you can do is just find any common denominator. The only advantage the LCD has for you is that you don't have to simplify in the end if you find the lowest common denominator. If you find just any common denominator, then you have to simplify after the fact. But I honestly think it's easier to just take whatever you have in the denominators and just multiply all of those things together. That's your common denominator. It might not be the lowest, but it is a common denominator. And then just multiply through and simplify. With an LCD, it's multiply through, no simplify. That's the only difference. So then we're going to take the entire numerator. In order to multiply this or keep this the same, we've got to multiply it by 1. So we're going to multiply both top and bottom by the LCD. Here it just so happens that the product of all of our denominators is the lowest common denominator, but it might not always be. So I don't know if that makes sense, but if you have like something like 1 over x squared plus 4 minus 1 over x cubed all over 1 over x squared, then I wouldn't try to factor, you can't really factor anything here, but I would just say, all right, well, my a common denominator here is just this denominator times this denominator times this denominator, and multiply through by that, and simplify after the fact. Does that make sense? I think it's easier in a lot of cases to do so. That way you don't have to factor and say, okay, well, this piece has this in common with this, and this other piece has this in common with that. What do they all three have in common? It can get kind of messy. So 9 plus h times 9, multiply that top and bottom. We've got two terms up top, so don't forget to distribute the 9 plus h times 9 to both of those terms. So on the top, what do we get? Do it this way. This times this would give us what?
72.
Yeah, if you need to think about this as 9 plus h over 9 over 1, and this is over 1. I don't know if that is conducive to think of it that way, but yeah. The 9 plus h cancels with this 9 plus h, and we just have this 8 times that 9. Okay, minus our second term up top will be what? well, this time the 9's cancel, don't they? And we just have the 8 times the quantity 9 plus h. Okay. And for the bottom, like we've always done, that thing that's approaching 0, that factor, that term, whatever, we're going to leave it alone. We're just going to leave the denominator as it is and say it's h times 9 times 9 plus h. Is everybody okay with what we've done? Are there any questions? So we have 72. This is important. You've got this -1 out in front. So don't say that's just 8 times 9 plus h. It's -8 times that quantity. So -8 times 9, -8 times 8, h rather. I'm going to run out of room, but hopefully see what happens here. So the 72's go away, then we just have a -8h up top. Now that h on top and the h on bottom will cancel out. Write this here. Yeah? So I'll just continue this up here. This is the same as the limit as h approaches 0. We've taken the function in front of the limit and we've simplified it. We'll go ahead and simplify it as we progress here. So have the limit as h approaches 0 on the function -8 over 9 times 9 plus h. And so now the issue of h approaching 0 isn't an issue anymore because as h approaches 0, our denominator there doesn't approach 0. So we can now evaluate that directly. Do it over here. We're just going to plug in, no issues now, so we're just going to plug 0 directly in for h. To get -8 over 81. Anyone have any questions on that? So I know we're just looking at specific examples, but these specific examples sort of give us the 3 main algebraic techniques that we have to compute limits. Either we can factor it, involve the conjugate, or involve the lowest common denominators for complex fractions. Yeah. Right, yep, so we've got a hole on this function at 0, -8 over 81. All right, try to get on MML and email me if you have any issues or questions about the homework. Honestly, that we've got 2 sections down. You should probably start some of the homework because it's kind of significant.